Okay, so let's look at the next page of our notes. We actually have our definition of thermodynamics. Remember I said thermochemistry and thermodynamics? Thermochemistry is kind of like beginner thermodynamics. We go into thermodynamics, chapter 15, 16, 17, something like that, second semester. And we come back to a lot of these same things. Okay? In thermodynamics, we have several laws. The first law of thermodynamics is that the energy of the universe is constant, which is another way of saying energy cannot be created nor destroyed, which is our law of conservation of energy. So, heat is a type of energy, and it's when we transfer energy because of a temperature difference. Heat and temperature are not the same thing, but they are closely related. So in like everyday usage, people use them, wrong and interchangeably, because since heat is a transfer of energy when there's a temperature difference, you are measuring a temperature in order to find a heat. And then we have work, which is force acting over a distance. Okay? If you stand here and push the wall, I don't care how long you push the wall, how tired you get, you have technically done no work, because there was no distance. But now, we're not going to be calculating work like that. We're going to have delta E, change in energy. That triangle is delta. That is a capital Greek delta. And it means change in. So if you see delta capital T, change in temperature. Delta lowercase t, change in time. Right here we have delta E. We'll see a delta H later on. We use delta a lot. Okay, so we have the change in internal energy equals heat plus work. Q, which is the heat, and I have no idea why Q is used for heat. Every time I get to this chapter, I go, why is Q heat? And I keep forgetting to look it up. Okay, so if Q is positive, it was endothermic, because the system, remember we're defining it in terms of the system is gaining the heat. Negative, it's exothermic because it's going out. Now the signs for work. W is positive when the surroundings do work on the system because work's going in. Heat goes in, Q is positive, work goes in, W is positive. And what they talk about most with this in the book is like a cylinder, like a piston and a cylinder. So imagine like that syringe we used for the pressure volume lab. If you're pushing that in, you as the surroundings are doing work on the system, the gas. When you took your hand off, the gas did work because the gas expanded and pushed it back out. Okay? So right here, we have Q, and we have W. Delta E is what we're looking for. And delta E equals Q plus W. But we weren't given these in just a list like you were in the homework. We have to look at, from the words, what our sign is going to be. 47 kilojoules of heat is released. So is that positive or negative? Negative. So we have negative 47 kilojoules. Okay? And 88 kilojoules of work is done on the system. So what sign does that have? Positive. Okay. Another thing to check with these, make sure your units match, because you can't add joules and kilojoules. So you have to make sure they're both kilojoules or they're both joules. And that goes for other thermo calculations we do. We'll see some problems, maybe not here, maybe in the next time we come back to thermo, where one of your values is in joules, one of your values is in kilojoules, and you have to make sure they match before you can add them. Okay, so we add those. And what do we get? Positive 41 kilojoules. Okay, which actually turns out that that's exactly the same thing as 31. Hey, but that's all we were doing in number 31, was just applying this equation. Now, when we have work done on a gas or by a gas in a cylinder, well, when you do work on a gas, this is what I was just talking about, when you do work on a gas, you're pushing the cylinder in, so you're making the volume do what? You have two choices, get bigger or smaller. If you're pushing it in, you're making the volume get smaller. When you let go, what does the system, what does the gas do naturally? It expands, and so it's making the volume larger. So, work done on a gas or by a gas in a cylinder is based on the pressure and volume. So, it's negative P delta V. So, what does delta V mean? Change in volume. Okay? What do you notice that you have to do with these two volumes? Yes, one thing you have to do is subtract. What else do you have to do? You have to change them to the same units. Okay? Now, we want our unit to be liters. Okay? And the reason we want it to be liters is because we need that liter atmosphere. Kind of like in our gas constant, remember our R was liter atmosphere per Kelvin mole? So we can convert it into something else when we have it in liters. So 5 milliliters, how many liters would that be? .005. This would have to be 5 milliliters times 1 liter over 1,000 milliliters. So dividing 5 by 1,000. Okay? So our delta V is V2 minus V1. So 0.005 liters minus 5 liters. Now we don't worry about significant digits until when? The end of a problem. Okay? So we're going to have negative 4.995, right? Okay. Of course, I have no idea why this doesn't want to let me write. I wish I could figure that out. Bad computer. All right. So we have then W equals 2 atmospheres times the negative 4. I'm just going to stop this. So do the math and finish that. And I'll try to figure out why my computer doesn't like me today.